exactly the same.
So what must be happening, Boyle guessed, was that the particles of water were moving further apart. And that was the expansion, not some substance flowing into the barrel from outside.
Boyle was becoming increasingly convinced that cold was not a substance, but something that was happening to individual particles, and he began to think back to his earlier experiments with air. As matter like air becomes warmer, it tends to expand. Boyle imagined the air particles were like tiny springs, gradually unwinding and taking up more space as they heat up.
Boyle's conclusion here was that heat is a form of motion of a particular kind, and that as bodies cool down, they move less and less.
Boyle's longest published book was on the cold, yet he found its study troublesome and full of hardships, declaring that he felt like a physician trying to work in a remote country without the benefit of instruments or medicines. To properly explore this country of the cold, Boyle lamented the lack of a vital tool, an accurate thermometer. It was not until the mid-17th century that glass blowers in Florence began to produce accurately calibrated thermometers. Now it became possible to measure degrees of hot and cold. Like the air in Boyle's experiment, heat makes most substances expand. Early thermometers used alcohol, which is lighter than mercury and expands much more with heat. So these Florentine thermometers were sometimes several meters long and often wound into spirals. But there was still one major problem with all thermometers: the lack of a universally accepted temperature scale.
There are all kinds of different ways of trying to stick numbers to these degrees of hot and cold, and they, on the whole, didn't agree with each other at all. So one guy in Florence makes one kind of thermometer, another guy in London makes a different kind, and they just don't even have the same scale. And so there was a lot of problem in trying to standardize thermometers.
The challenge was to find events in nature that always occur at the same temperature and make them fixed points. At the lower end of the scale, that might be ice, just as it begins to melt. At the upper end, it could be wax, heated to its melting point. The first temperature scale to be widely adopted was devised by Gabriel Daniel Fahrenheit, a gifted instrument maker who made thermometers for scientists and physicians across Europe. He had several fixed points. He used a mixture of ice, water, and salt for his 0 degrees, ice melting in water at 32 degrees, and for his upper fixed point, the temperature of the human body at 96 degrees, which is close to the modern value.
One of the things that Fahrenheit was able to achieve was to make thermometers quite small. And that he did by using mercury, as opposed to alcohol or air, which other people had used. And because mercury thermometers are compact, clearly if you're trying to use it for clinical purposes, you don't want some big thing sticking out of the patient. So the fact that he could make them small and convenient, that seems to be what made Fahrenheit so famous and so influential.
It was a Swedish astronomer, Anders Celsius, who came up with the idea of dividing the scale between two fixed points into 100 divisions.
The original scale used by Celsius was upside down. So he had the boiling point of water as 0 and the freezing point as 100, with numbers just continuing to increase as we go below freezing. And this is another little mystery in the history of the thermometer that we just don't know for sure. What was he thinking when he labeled it this way? And it was the botanist Linnaeus, who was then the president of the Swedish Academy, who after a few years said, well, we need to stop this nonsense, and inverted the scale to give us what we now call Celsius scale today.
A question nobody thought to ask when devising temperature scales was, how low can you go? Is there an absolute lower limit of temperature? The idea that there might be would become a turning point in the history of cold.
The story begins with the French physicist Guillaume Amonton.
Its pressure.
He was doing experiments, heating and cooling bodies of air to see how they expand and contract.
Amonton heated air in a glass bulb by placing it in hot water. Just like a hot air balloon, the air in the glass bulb expanded as the increased pressure forced a column of mercury up the tube. Then he tried cooling the air.
He was noticing that, well, when you cool a body of air, the pressure would go down. And he speculated, well, what would happen if we just kept cooling it?
By plotting this falling temperature against pressure, Amonton saw that as the temperature dropped, so did the pressure. And this gave him an extraordinary idea.
Amonton started to consider the possibility, what would happen if you projected this line back until the pressure was zero? And this was the first time in the course of history that people had actually considered the concept of an absolute zero of temperature. Zero pressure, zero temperature.
It was quite a revolutionary idea when you think about it, because you wouldn't just think that temperature has a limit of a lower bound or zero, because in the upper end it can go on forever, we think, until it's hotter and hotter and hotter. But somehow maybe there's a 0 point where this all begins. So you could actually give a calculation of where this 0 point would be. Amonton didn't do that calculation himself, but some other people did later on. And when you do it, you get a value that's actually not that far from the modern value of roughly minus 273 centigrade.
In one stroke, Amonton had realized that although temperatures might go on rising forever, they could only fall as far as this absolute point, now known to be minus 273 degrees centigrade. For him, this was a theoretical limit, not a goal to attempt to reach. Before scientists could venture towards this 0 point, far beyond the coldest temperatures on Earth, they needed to resolve a fundamental question. By now, most scientists defined cold simply as the absence of heat. But what was actually happening as substances warmed or cooled was still hotly debated.
The argument of men like Amonton relied completely on the idea that heat is a form of motion, and that particles move more and more closely together as the substance in which they're in gets cooler and cooler.
Unfortunately, the science of cold was about to suffer a serious setback. The idea that cooling was caused by particles slowing down began to go out of fashion. At the end of the 18th century, a rival theory of heat and cold emerged that was tantalizingly appealing, but completely wrong. It was called the caloric theory, and its principal advocate was the great French chemist Antoine Lavoisier.